Today we're going to take a look at some properties of log functions. And remember, because the log is the inverse of an exponential, the properties of exponents relate very closely to the properties of logs. So looking at our first property of exponents, if we have a power times a power, we add the exponents. Remember, the answer of a log function is an exponent. So when we look at our first property of log, if you are adding exponents, it comes from multiplication. So if you have log base a of x times y, you can split that up as log base a of x plus log base a of y. Our second property of exponents. If you are dividing powers, you subtract the exponents. So over here we have subtraction of exponents, which came from division. So log base a of x divided by y equals log base a of x minus log base a of y. And then our last property of exponents is a power to a power. You multiply the exponents. So if you are multiplying exponents, it came from a power. The last is the change of base formula, and we'll come back to that a little later. All right, so starting by condensing to evaluate. So looking at our first question, log of 40. Remember, if we don't see a base, it's base 10. Log of 40 cannot be evaluated exactly, and neither can log of 25. But let's see what happens when we condense them. So if we are adding logs, we can condense it to a single log and multiply what we're taking the log of. 40 times 25 is 1,000. This we can evaluate exactly without a calculator. 10 to what power equals 1,000? 3. So log of 1,000 equals 3. Our next one, we have a number times a log. What that means is we can make that coefficient an exponent on what we're taking the log of. So this becomes log base 4 of 8 squared, or log base 4 of 64. 4 to what power equals 64? 3. Last example on this page, we've got subtraction. When we condense that, we condense it to division. So we've got log base 3/2 of 12 divided by 18. We still can't calculate that exactly, so I'm going to simplify my fraction to 2/3. And now we think 3/2 to what power equals 2/3. So what power will flip my base? And that's a negative exponent. So log base 3/2 of 2/3 equals -1. Now we're going to take a look at the property of inverses. So we've got an exponential function base 2 raised to log base 2. Those cancel each other out. They undo each other. They are inverses. So that leaves us with 12. Same principle on part B. Log base 5 of an exponential base 5. Those will cancel each other out, leaving us with x divided by 3. All right, now we're going to take a closer look at the change of base formula. And what I want to do for you is show you why the change of base formula works. So we're going to convert log base a of x to a common log, or a log base 10. So we start by setting it equal to y, and then using the curly law to turn it into an exponential. So a to the y power equals x. Now, you're going to be a little confused as to why I'm doing this next step, but just follow me through till the end of the proof and you'll see why. Remember, my goal is to convert this to a common log. So now I'm going to take the common log, or log base 10, of both sides. You might wonder why I'm putting it back to a log when I just converted it to an exponential. Again, my goal is to finally get this as a single common log. Now what I'm going to do is use the property of exponents, where if I'm taking the log of a power, I can make that power as a coefficient. So I'm going to rewrite or expand my first log as y times log of a equals log of x. And I want to solve for y, so I'm going to divide both sides. Here's why I'm solving for y, because the first thing I did was set my log function equal to y. So I'm going to use some substitution at the end to show you how they're equal. So I'm going to divide both sides by log of a. So we got log of x divided by log of a. And finally, my goal was to convert my original expression to a common log. My original expression, like I said it equal to y. So now I'm going to substitute log base a of x for y because they are equal to each other. Now, for those of you who are freaking out that I might actually ask you to do a proof, that's not why I did this. I wanted to show you why the change of base formula works instead of just giving it to you and saying, here's this cool formula that works and we're going to use it now. Here is why it works. So log base a of x equals log of x over log of a. You can change any log to any other base using this change of base formula. So I'm going to jump back up here, and that's exactly what I did right here, was prove that that works. And we changed it to a log base 10 or a common log, which to be perfectly honest is the one that you're going to use because that's the one that your calculator knows. But again, you can change it to any base. So here's the way to remember the order that this change of base formula works in. The base, when you write a log, is lower, so that goes in the denominator. What you're taking the log of is higher, so that goes in the numerator. They kind of stay in their respective places. So we're going to use that change of base formula to evaluate some logs that we otherwise can't. Because 4 to what power equals 30? There's nothing. We can't evaluate this. So we use our change of base formula to the common log. So the 30 is higher, so that goes in the numerator. The base is lower, so that goes in the denominator. And then you punch those buttons on your calculator. If you don't know where the log button is, we can look at that in class. But if you want to double check and make sure that you're evaluating that correctly, I got about 2.453. And our next one again, what you're taking the log of goes in the numerator. The base goes in the denominator. And then you do log of 14 divided by log of 2 on your calculator and get 3.807. Again, any calculator issues, we'll clear those up in class. And your U-try questions.